Oh, it's a little hard to know just how to change gears from that back to our next event here. But I think it is going to be just about time to bring on our next speaker.
Yeah, so and this is our last speaker of the day, is that right?
Right.
It's been sort of an amazing day. There's been a lot of people talking about a lot of really cool stuff.
So who wants to dive into the intro here for Mr. Tim Pennings?
I'm happy to do it. I'm happy to let Tarina do it. You can do it, whatever. I don't know. We can do whatever we want, huh?
It's the power of hosting.
We have the power. Go ahead, Tom.
All right, I'm happy to introduce Tim actually because so I can say something a little bit about Tim too, and then I can give the real introduction. But real quick about Tim, I met Tim a number of years ago, but last year we participated in this event last year as well, and Tim was nice enough. There wasn't sort of the interactive version that we have this year on the website, so Tim was nice enough to stick around during my talk and to provide me some feedback and participate with me. So I was very appreciative of that. So the next speaker that we're going to hear from is Tim Pennings. He received his PhD from Iowa State University, where he recently received the Distinguished Alumni Award. He taught at Hope College in Holland, Michigan for about 25 years, and then served for 9 years as the chair of the math department at Davenport University. His professional interests include the rich stuff in the confluence of mathematics, physics, theology, and philosophy, especially the infinite. His initial research in discrete dynamical systems morphed into using differential equations to model various natural phenomena, including bicycle dynamics, optimal kayaking strategies, and most famously, which is the first time I encountered him, was answering the question, do dogs know calculus? And do dogs know bifurcations? For article that he received the MAA George Polya Award in writing, and apparently a letter from the Queen of England. So not to be outdone, though, his dog, the Welsh Corgi Elvis, received an honorary doctorate. And so I think we're going to hear from Tim next. So I don't know if we can bring Tim on or whatnot. And Tim's talk is going to be about the Battle of Titans, math versus truth. Is that right, Tim?
Very good. Yes. And before I get to the talk, let me kind of jump on a couple of things that have just been said. Piggybacking on what Ruth said, Christopher Havens, we've gotten to be friends over the last year. In fact, just real briefly, about 5 years ago, I read a article in GQ magazine of all places that talked. The title of it is "Buried Alive: Stories from the solitary confinement." And anyone can find it very easily on the web. Just Google that and you'll find it. But it said that on any given day in the United States, 90,000 people are in solitary confinement, some of them for 15, 20, 25 years, which just floored me. And it just got me passionate about what can I do. And I eventually, then about 2 years later, I happened to read this article in Popular Mechanics about Christopher Havens. And I thought it had the address. I sent the email. I got a letter back from Chris the next day. And within a month, I was mentoring another inmate. And Christopher and I have become good friends. And we talk and whatnot and write letters back and forth. But he's given me a draft of the book that he's writing, and this is just one paragraph from it that dovetails with what Ruth was saying. I just want to read it. It's powerful. He writes this: freedom is not the ability to come and go when one chooses. Freedom is being able to accept and love yourself while doing the things that bring you true happiness. I achieved this inside a small concrete box. I had never accepted nor loved myself, nor had I engaged in things that brought me true happiness. I was in prison in my youth, on a socially unacceptable quest to be cool. Ironically, this very thing would lead me straight to prison, where I would find true freedom. And I get choked up just reading that again, but it's powerful, just powerful stories in there about him and his life before prison and during prison and so on. Extraordinary person. So I'm just super privileged to be part of the prison mathematics project and to contribute to it financially and everything else. I mean, it's easy to do. It's a good use of time. So that's my plug for it. So I'll say that. The other thing before I start my talk is you were talking about Fibonacci sequences with Amy. I had the New Holland Brewery Company. Some of you might have access to their beer. They're from Holland, where I live, and they called me up, I don't know, maybe about 10 years ago, and said, we want to develop a Fibonacci brew. Can you help us? And so I went and talked to the owner, and I found out they had about 4 different ingredients. And so using the right kinds of units, I said, well, make them in the ratio of 1, 1, 2, 3. And the next year you can just shift it to 1, 2, 3, 5, and it can be a little bit different every year, which is what they wanted. And so I've got a Fibonacci brew named after me. I have that as one of my publications on my CV, the Fibonacci brew. So so much for that. And the last thing, quick, is as a nod to Pi Day, here's a question for any of you. Tom, you might remember this because I think I asked the same thing last year. Do any of you know of something involving a circle which does not include pi? So something involving, of course, the sphere, the surface area, all those things have a pi in them, the area, all that stuff. But it turns out that if you take a point on a circle with radius 1 and you roll that circle down a line, so that then you take the arc of it, which is called the cycloid, it turns out that cycloid, the length that little dot goes to until it hits the paper again, that's exactly 8 units long. So there's no pi in there. So to me, that's really kind of extraordinary that there's something involving a circle which does not have a pi in it. So for what it's worth.
And before you get started, in terms of pi not showing up, we almost got through the day without any actual PIE showing up on the telecast. But I'm going to apologize. I'm not going to be able to stay till the very end of your talk, Tim. I'm going to start listening to it, and I'm going to enjoy that with my slice of blueberry crumble right here. So.
Very good. Thank you, Glenn.
Thanks for joining us, Glenn. Yeah, and Tim, thanks. And Tarina and I will be, I think, sticking around through your talk if you have any questions for us or anything. But otherwise, we'll let you take it over. Does that sound right, Tarina?
That sounds right.
Okay.
We're hanging out.
I'll get it going here. Let's see. Okay. Can you all see me and see my slide? I think you should be able to.
Yes, we can see you.
Oh, very good. Okay, thanks. Okay, so this is actually a compilation of a couple talks that I made when I was at Davenport University for the whole campus, for all the faculty, and yeah, I guess just all the faculty. So it's meant for a non-mathematical audience. But when I think about it, a lot of mathematics students, this would be a very valuable talk for them to hear. And so I throw it out there for people who are listening to part of this conference that are either mathematicians or non-mathematicians, or if you happen to be a teacher and you want a copy of the PowerPoint, I'd be glad to give it to you and you can pass it on to your own students. But it's kind of a bird's eye view of the history of mathematics over a couple thousand years here. And you'll see how it relates to truth. So first part, Euclid to Einstein, how eggheads changed history. So Euclid, about 300 BC, was the first person to really kind of be bothered by this question, how do we know? And he applied it in particular to geometry. And so there'd been all these geometric rules for hundreds of years, probably thousands, such as if you take a couple parallel lines and slice it through, then those interior angles add up to 180. There are about 470 of those things that they had developed over time. And they had used those to build all sorts of things, right? Furniture, the Parthenon, the pyramids of Egypt, and everything else. So they had been used. And no one ever doubted that they were true. And so Euclid was this kind of modern person just by asking this question, how do we know it? And so by systematically looking at it, he realized you didn't have to assume that they were all true. You could only assume that there were 5 of them that would be true. And then if you use just deductive reasoning, you could get the rest of them. And so those 5 that you need to, as kind of your initial axioms, that anyone who's had geometry knows these. The first one is that 2 points determine a unique line. Once you have that line, there's only a unique way to extend it. If you have a point and then a length for a radius, that's going to determine a unique circle. And this one seems kind of strange, but all right angles are equal. And then the last one, given a line and a point not on that line, there's a unique line that passes through the point that will never intersect. That is, it's parallel to the original line. Okay, so through the century, geometry was held up as the supreme example of truth. Its foundation was these 5 indisputable facts. All the other 465 could be deduced from these through just mathematical deductive logic. And finally, it worked, right? The proof was in the pudding, so no one had any reason to doubt it. Okay, it was considered the prime example of truth. So it was thought this way for thousands of years. Okay, just as the philosopher Immanuel Kant was claiming that geometry was the prime example of truth, a little cloud appeared on the horizon. Okay, so what happened? The problem is mathematicians didn't like that 5th axiom. Okay, if you look at it, you notice already, just in the way I read it, something's different from it than the first 4. Look how long it is. Not as easy to state, not as obvious, since you're talking about things going on forever, never meeting, even though they go on forever. No one doubted that this was true. It's just that, doggone it, if you wanted these if you wanted these indisputable facts to build all of geometry on, you just assume not have to have that 5th one. If you could just have those first 4, life would be much better. So that's what they set out to do. Okay, they said, hey, let's see if we can prove that 5th one from the others. And so they spent hundreds of years doing this, and one attempt was trying to do it by doing a proof by contradiction. And so they said, okay, he said, okay, let's use this as the starting assumption that all lines intersect, or that no lines are parallel, that all lines are going to intersect. You don't have any set of parallel lines. And let's see what happens if we start with this. And when they started with it, he found out that they got this, what he considered a contradictory result, that the sum of the triangle, that the interior angles of a triangle sum up to something not equal to 180. And so set this off and said, aha, apparently this was a wrong assumption to begin with. Therefore, apparently the 5th axiom is in fact true, because if we assume it's not true, then we get this contradictory assumption. That worked for a little bit, but then came along Carl Gauss, and he shook the world when he was the first to realize that changing the axioms of geometry were just like changing the rules of a board game, such as chess. As long as the axioms were self-consistent, they just resulted in a different but equally good game. So the point is, Gauss realized there was no contradiction in getting that conclusion that the sum of the angles added up to something greater than 180. There was no contradiction. It was just something that people assumed was wrong, but there was no contradiction. It was just a different geometry. And with that realization, it literally shook the world. I mean, and I'll give you a quote here in a minute, that just our whole thinking about truth changed. Okay, and as a result, the world changed. Okay, just to be clear, before, geometry was used by Kant, by all these philosophers, scientists, theologians, mathematicians down through the centuries as the prime example that truth existed. It rested on these sure axioms. The deductive method was used to get it. It was totally self-consistent. The results from the real world verified it. What more could you ask for? What does it mean to be true except for satisfying those properties right there? Does truth exist? Of course. Just look at geometry. Okay? But now, after Gauss's realization, he realized, no. Euclid's geometry is just one example of many possibilities. Just because something is self-consistent doesn't mean it's true. The board game chess is consistent, but we don't say it's true. It's just a game. Okay, so something can be consistent without being true. Okay, so he pulled those things apart. Okay, that was a key thing he realized. Just because something is verified by experience doesn't mean it's true. Okay, Karl Popper is the 20th century philosopher of science who was the first to kind of really elucidate the fact that just because the way he said it is science never proves anything true. It just proves things false, right? It's like flipping a coin. If you keep flipping a coin over and over and you keep getting heads over and over and over again, you get more and more probability that maybe it's a two-headed coin, but you don't know for sure. As long as you're just doing these experiments, you don't know. The next experiment could be the one that falsifies your statement, your hypothesis. So the point is, all these things that were kind of all wrapped up with being true were all teased apart. Being self-consistent isn't enough. Being verified by experience isn't enough. It brought the whole question of what does it even mean to be true, brought that right to the surface. And so, as I say, that's really what kind of changed the world with that realization. And here's an extended quote by Morris Klein, who is again a 20th century mathematical philosopher. So I'll read it here. All people prior to non-Euclidean geometry had shared the fundamental belief that man can obtain certainties. The solid basis for this belief had been that man had already obtained some truths, witness mathematics, geometry in particular. No system of thought has ever been so widely and completely accepted as Euclidean geometry. Men such as Plato and Descartes were convinced that mathematical truths were actually innate in human beings. Kant based his entire philosophy on the existence of mathematical truths. But now philosophy is haunted by the specter that the search for truths may be the search for phantoms. The implication of non-Euclidean geometry, namely that man may not be able to acquire truths, affects all thought. Past ages may have sought absolute standards in law, ethics, government, economics, and other fields. They believed that by reasoning, one could determine the perfect state, the perfect economic system, the ideals of human behavior, and the like. The standards sought were not just the most effective ones, they were the true, unique, correct ones. Our own century is the first to feel the impact of non-Euclidean geometry because the theory of relativity brought it into prominence. It's very likely that the abandonment of absolutes has seeped into the minds of all intellectuals, not only all intellectuals, but all people. We no longer search for the ideal political system or ideal code of ethics, but rather for the most workable. Morris Klein wrote that and published it in 1967. Josh McDowell is an interesting man. He has spoken on probably more college campuses than maybe anyone else alive. He's probably in his 70s or 80s at this point. He is a Christian speaker who speaks on his belief that Jesus rose from the dead and the truth claims of Christianity. I heard him back when I was in college in 1976, and then he came to Holland, maybe 10 years ago, after a whole generation or more of being on college campuses. And he made a real interesting comment. He said back in the 70s, when he would speak on these college campuses, students would raise their hands and object, and they would say, "Mr. McDowell, you're wrong." That would be their objection. "You're wrong." And he says, now, a generation later, they raise their hands and they say, "Mr. McDowell, you're not being tolerant." It's just really interesting. It gets at the heart of this thing, that the whole question of truth is just not as important of a question as it used to be. It's become other things. Not that there's anything wrong with tolerance, obviously, or any of that. But the point is, it just shows how this has maybe started with Gauss and how that has kind of seeped. Just like the ripples of a pond is seeping out through time and through the disciplines and through intellectuals, through the common folk. So anyway, kind of interesting. So let's look at the mathematical portion of it. How can there be different geometries in Euclid? And I won't spend too much time on this because I assume a lot of the readers probably already know this, unless you're happen to, well, I don't know. I'm not sure who the listeners are. So consider a globe. Okay, there's another surface. As with a plane, A straight line on a globe is the shortest distance between 2 points. So what you do is you take yourself a globe and you take a rubber band and you just stretch it between 2 points. And so if you go from Grand Rapids, Michigan, where my nearest airport, to London, England, and you stretch it tight, it won't go along the latitude line. Instead, it goes up north through Greenland. And that's why if I fly over to London, I can look down at one point and see Greenland under me. And so the straightest distance is what a straight taut line will take. It's called a great circle. So yeah, that's what I say in the second point. So the equator and longitude lines, they're all straight. Okay, you could take a rubber band and put them along there and tighten them up, and they'd stay right along the longitude line, right along the equator. But if you try to put it along the Tropic of Cancer, Capricorn, or any of the other latitude lines and pull it straight, you'll see that it won't stay put, right? It'll collapse to a point. And so that's because those are not straight lines. So if you realize that, then you think of a globe, and there you have a picture of a globe with a bunch of straight lines on it. You'll see that any two straight lines are going to intersect. Okay, there's no parallel lines. Any two will intersect. So it's really kind of amazing when you think about it that we had trouble imagining other geometries when in fact we live on the surface of another geometry than Euclidean. But anyway, obviously on a smaller level, it feels like a plane. So that on a local level, it feels like a plane. So that's what it feels like. But the point is, you look at a globe. There's the middle one there shows it, and then the last one over to the right shows a nice example. There's a triangle. You see the triangle there? You have 3 dotted lines. Those are all straight lines. And you see that when you look at the interior angles of that triangle, they're going to add up to 270 in this case. Okay, so no matter what triangle you put on a globe, it's going to end up being greater than 180. So there you go. Okay, so that's all spherical geometry. So then that raises the question, okay, given that there are these different kinds of geometries, the ones I just showed you were all on a two-dimensional surface. What about the world we live in? It's three-dimensional, but the same question applies. Do we live in a three-dimensional world in which basically if you were to take these straight lines through space and connect them together, that you would, if you look at the interior angles, would they add up to greater than 180, or would they add up to exactly 180 if you did it through space? And as I understand, I think at one point in history, people actually tried doing that using surveyor transoms on mountaintops. The problem is it's like doing it on this table. It's much too small of a triangle. You'd have to get out there very, very far, look at astronomical distances and such. And so it's still an open question. But here's where it becomes so interesting, because a straight line in space is basically a beam of light. A beam of light, just like that taut rubber band, it wants to get from one spot to another spot as quickly as possible. Okay, so a beam of light is a straight line. And so Einstein took that, and here's what he did with it. Okay, let me put it down first. He said, okay, this is where if I were in the room with all of you, it would be easier. But I'll see if I can do it with my hands. I assume you can see my hands here. So basically, imagine yourself in a room with just a box, no windows or anything like that. And you're just in this room, and you and your friends are there, and you're just on the floor, you're playing gin rummy or something like that. Okay. And you're being pulled down to the floor. Now you take that box, you take that room, and you lift it up into space, and you fling it up into space, and it's just floating around in space. So now there's no gravity at all. You're just kind of floating in space, and you're just kind of bouncing from side to side and bouncing off each other and having fun being weightless. Okay, so you're weightless for a couple days, but now all of a sudden you find yourself being pressed down to the floor again. Okay, what one side or another, you're all being pressed down. Einstein realized one of two things might be happening. Either you have landed on another planet, hopefully not the sun, and by the gravity of that planet is pulling you all down with its gravity. That's one possibility. The other possibility is that maybe there are jet engines on one side of the room, which are blasting, and they're accelerating you. And as they accelerate you up, you are being pressed down on the ground. Okay. So the first realization that Einstein had is we can't tell the difference. We can't tell the difference between being accelerated or being under the influence of gravity. Okay. We can't tell the difference. That's number one. Number two, then he asked himself this question. If you have a little hole in the wall on one side of this room, and you let a little light beam go through that hole, and it shows up on the other wall, okay? So it goes through and it shows up on the other wall. There it is, okay? Now, Einstein asked himself this question. He says, if suddenly you were to accelerate that room, how would that light beam change? And of course, the answer is, if you're accelerating upwards, that light beam, it goes through here. The room is being accelerated upwards so that by the time it hits the other wall has raised a little bit. So from your perspective in the room, it looks like the light beam is bending down. Okay. So then Einstein put these two thoughts together and he said, okay, I can't tell the difference between gravity and acceleration. That light should not be able to tell the difference either. So since acceleration would make that beam of light appear to be bending down, gravity must also make it bend down. The light shouldn't be able to tell the difference any more than you and I could. And so Einstein theorized that if you have a big enough object with strong enough gravity, it's going to bend light to a discernible amount that you'll be able to recognize it. The problem is we don't have anything large enough to have that much mass to bend light, because it would take so much mass. The only thing close to us is the sun. Well, that works well because there are stars on the other side of the sun. We know exactly where they are in space. So we know exactly when we should be able to see them as they come around the sun. If in fact, here, I don't know, I hope you can see me here. Here we are. Here's the sun. Here's the star. If there's no bending, you're not going to be able to see the star until it comes off the edge of the sun so that we can see the light. On the other hand, if it does bend, even with the planet being here, what's going to happen? That light's going to go this way. The sun is going to bend it, and we're going to be able to see it, even though the position of it is here. So we're going to be able to see it earlier than we think we would as it comes around the sun. So there's a great way to check the problem. The practical problem is, though, how are you going to see the faint light from the star with the sun's light in the way? And of course, the answer to that is you wait until the light of the sun gets blocked out. So this was during World War I. There was a solar eclipse, and I think it was 1919, if I'm not mistaken. Is that right? Anyway, and so they went all around the world, even though this was in the middle of World War I, and they put up these measuring telescopes and such, because you never know where there's going to be clouds, and so they wanted enough of them for redundancy. And sure enough, just as Einstein had predicted, they saw the star before they were expecting to, and that's when he became famous. That's when he became a household word, was when they realized, that's basically general relativity there. So that's all very cool. So that all comes with this question of different kinds of geometry. So it's just neat how it's all connected. Okay, so there's that. Okay, so what's the recap? Discovery that there are geometries different from Euclid has changed the way we understand both our physical world. Our three-dimensional space may be flat or it may be curved. We don't know. It also changes our mental world. True is not always an appropriate adjective. What does it mean to be true? Okay, so that's one kind of overview of mathematics. And then here's a continuation of it. Okay, so I'll take a quick gulp. Okay, here's Descartes. Okay, here's Descartes. He's known for two revolutionary ideas. Do you know what they are? The first one, I think, therefore I am. The second one, the Cartesian plane. I love to tell my students when in calculus or pre-calc or algebra, when I put the plane down and mention this is a Cartesian plane, it gives me a chance to give them a whole little 5 or 10 minute talk on Descartes. And I teach them something without them even realizing it. It's a wonderful, what I'm going to tell you now is what I tell them. Okay. So Descartes did the same thing that Euclid did. Euclid asked this question about geometry. Is it true? How do we know? Descartes said the same thing about everything in life. How do I know for sure? What do I know for sure? Can I trust my memory? Can I trust my experience? They both are fallible. It turns out the only thing I can say for sure is, well, doggone it, I'm thinking right now. I'm not sure what I am, but I'm thinking, and if I'm thinking, then I have to exist. And so that was his founding axiom, just like Euclid had a founding five axioms. Descartes, this was his founding one. And as I say, he realized he can't rely on his experience or memory or anything else. And just to drive home this point, I want all of you that are watching this talk to just do this simple little problem. I'll read this for us. Finished files are the result of years of scientific study combined with the experience of many years. Would you all just take a moment and count the number of F's in that sentence? Just count the number of F's in that sentence. And there's only a couple of you who I can hear. So if one of you, Tom or Glenn, whoever's still there, or
let's see. I tried to count them, but now you put me on the spot, and I'm afraid that I'm gonna miss some. But I caught 3 F's.
And who's this talking?
This is Tom.
Tom, isn't it amazing that there are some people who can't count them all? It seems obvious. It seems easy, doesn't it?
I'm very nervous. I'm sure I missed one. Tarina's here as well. So
Tom, don't try to put me on the spot. But I count 3 as well.
Okay, so you both count 3. So are you both pretty sure then that you got them all?
No, when you ask
I
a
didn't know
question
I
like
was
that,
at the
we
count.
are not.
I didn't know I was at the count.
Well, count them again just to make sure. I mean, just the whole point of this is, can we trust our experience, right? So there's nothing fancy about what I'm saying. Just
no, I see. I caught a 4th one, man. I caught a 4th one on closer investigation. I caught a 4th. So now I'm not even sure there's 4. Maybe there's 10.
Well, count one more time, both of you.
I got a 5th one now, Tim. I caught a 5th one now and a 6th. I got a 6th one now.
And who's there with you?
That's Tarina's here as well.
Tarina, do you still count 3?
Hey, I'm sticking with 3, Tim. I'm sticking with 3.
Well, you two are a great audience, because that's exactly the way it breaks up. Tom, tell Tarina the 3 that she's missing.
I would guess she's missing the of, because as soon as I caught an of, I saw 3 ofs, but I had to really focus.
Oh, wow. Yes. You are right. That's exactly what I missed.
Isn't that amazing? So I have little slips of paper with this, and I give them to people, and I've gotten more Snicker bars, I've won from this thing. And the reason, just to let you know, the reason why you miss the ofs is not because it's a small word, but it's because even when I read that, notice what I did. I said, finished files. You're counting the number of times without realizing that you make the sound. And then the of is a V sound. And so it goes right by you. Isn't that amazing?
Totally amazing. Yes. And I'm glad, Tarina, that you were there with me miscounting the 3. I'm sorry.
Well, anyway, here's another one. And this one, just every time I see it, it boggles me. And we're not there presently, so I can't do it. But I've got a piece of paper where you just cut out these 2 shapes. You cut out the orange top, and you cut out or it doesn't even matter. You can just cut out the orange top and take that piece of paper, and that will lie exactly over the brown top. It fits it exactly. And
no, I'm gonna call you on that one. Okay, I trust the F's, but I'm gonna call you on that one, Tim. There's no way.
all I can say is, because I can't do it physically for you, but go to Google and just put in a tabletop illusion or something like that. And then you can, after my talk, obviously, and then you can print it out. And once you print it out, you go ahead and cut it out. And even looking at it now, it seems impossible, but you'll be amazed. So it's just another example where
Truth isn't obvious, right?
Yeah, no, that's right. So anyway, thank you both. So anyway, that's his foundation was, I think, therefore I am. And so, as I say, it was the same sort of thing that Euclid did with geometry. And the point is, he started mathematicians asking, what of mathematics do we know? Not only about geometry, but what about all these other fields, algebra, analysis, probability, and so on. What about those is true? And so over the last couple hundred years, that's been kind of a question that's bothered scientists in general. So Frege was the first person who really started wrestling with it. And it took him, he started with sets. He started with simple as just sets. And then he used sets to build numbers and arithmetic. And he figures this is really the foundation of mathematics, if anything is. And so he started with that, and he worked for 12 years. And in 1903, just as the second volume was going to the printer, he gets a letter from, who's that? There's Bertrand Russell. So Bertrand Russell writes him a letter and says, Mr. Frege, I've got a question for you. You're talking about sets as just these kind of naive things, collections of things. Okay, he continues on. He says, some sets are members of themselves and some aren't. For example, the set of all trees is not itself a tree, but the set of all ideas is itself an idea. So some sets are members of themselves. So he asked this question. He said, what if you take all the sets that are not members of themselves? Is that set a member of itself? And it takes way too much time to think through it carefully here. But it's very similar to what's called the barber paradox of a barber in town, a man in town who proudly puts a sign in his barber shop that says, every man in town that does not shave himself, I shave him. I shave exactly the men in town who do not shave themselves. He's proudly saying, I shave everyone who doesn't shave themselves. And then someone realized that can't be right. And you might realize, oh, why can't it be right? Because who shaves the barber? If he shaves himself, then he doesn't. If he doesn't shave himself, then he does. So it's that sort of an inherent contradiction that Bertrand Russell discovered in Frege's naive set theory, which was the foundation for everything he did. And Frege wrote in his second volume, a scientist can hardly meet with anything more undesirable than to have the foundation give away just as the work is finished. In this position, I was put by letter by Mr. Bertrand Russell as the work was nearly through the press. What a lament. Russell took no joy in this at all. He wanted to find truth like no one else. He spent his life trying to find truth. And so he, along with friend Alfred Whitehead, a philosopher, tried to see if they could actually shore up and build this foundation, which was lacking from just starting with sets. So he started with logic. And if you look, I don't know if you can see my cursor or not, but on page 360 of volume 2 of this kind of stuff, so 500 pages of this kind of stuff, look at the very bottom to where he finally gets 1 + 1 is 2. So there's how much effort it took just to get there. And so in a sense, it was success, but it wasn't at all what Russell was hoping for. He wanted something much simpler than a book that no one else would ever read. And so he lamented, I wanted certainty in the kind of way in which people want religious faith. He wrote a famous book, Why I'm Not a Christian. I thought that certainty is more likely to be found in mathematics than elsewhere, but I discovered that many mathematical demonstrations which my teachers expected me to accept were full of fallacies, and that if certainty were indeed discoverable in mathematics, it would have to be a new field of mathematics with more solid foundations than those that had hitherto been thought secure. But as the work proceeded, I was continually reminded of the fable about the elephant and the tortoise. Having constructed an elephant upon which the mathematical world could rest, I found the elephant tottering, proceeded to construct a tortoise to keep it from falling. But the tortoise was no more secure than the elephant, and after some 20 years of very arduous toil, I came to the conclusion that there is nothing more than I could do in the way of making mathematical knowledge indubitable, knowable. Okay, so it gets that, again, the heart of my the talk, mathematics versus truth. What do we know for sure? How do we know it? So Trina or Tom, I don't know if either of you have ever been in a position like this in a restaurant where the waiter comes to you and you say, the mathematics seems correct, yet I find myself haunted by the idea that the basic axioms on which mathematics is based might give rise to contradictions, which would then invalidate these computations. I don't know, maybe you got a lesser bill for
It never worked for me. I didn't try it yet, but I guess maybe next time. Maybe next time.
Yeah, it hasn't worked for me either.
Marina, did you have any luck with it?
I did not.
Well, there you go. So anyway, then of course along came Gödel, a good friend of Einstein. By the way, as long as I've got it right here in my house, let me see if I can find it really fast. This is a book I would recommend to everyone. When Einstein Walked with Gödel, Excursions to the Edge of Thought by Jim Holt. I don't know if you can see that or not. Fantastic book. I just picked it up in our town bookstore. It was on the front table of the bookstore. Fantastic. This guy, he knows more ins and outs about mathematicians and funny stories and everything else. It's a wonderful book. But anyway, Gödel, of course, took this even further and showed that mathematics is there's always going to be some true things that can't be proved. So you have that. So then I extend this. I like to take mathematics and tie it in with theology and ethics and religion and philosophy and everything else. So to me, this is a next question. I say this many things can be written as 7 in base 10, or it can be written as a 1 and 2 in base 5, or 2, 1 in base 3, or 1, 1, 1 in base 2. And now, after Amy's talk, I realized you could have it in, where each of those digits is a different base. I've never even thought of that. So the point is, you have all these different ways to express something in different bases. And that blew my mind when I first saw that as an 8th grader. I had thought, there was only one way to do it. So to realize that this number 7 is just a convention and that we just happen to use it because we have 10 fingers. If we were the Simpsons, we'd be using base 8. That just blew my mind. It just, and so the point is, it seems like an absolute, but it's totally convention, okay? On the other hand, this many things can be put into equal size groups. There's 6 of them there. Whereas the above with 7 can't be put into equal size groups. That has nothing to do with convention. One of those numbers we call prime and the other one is not prime. That's an absolute. That would be true whether or not humans ever existed to think about it. It would be true wherever, even if there weren't a material universe. Okay, so there's something absolute about that. So the point is, in mathematics, you have some things which are convention, some are absolute. It gets to the whole question of, is mathematics created or discovered? That's actually something that Christopher Havens is dealing with the prison, because as I understand from some of the things he's told me, they told him at least at one point that the things he does and thinks about in prison belong to the prison. And so they belong to the prison, to which he responded, no, these things, if you find a pot of gold or what, I mean, he basically said, no, these aren't my inventions. These are there to be discovered. So he really got into the same question with the prison that philosophers deal with. Dang, interesting life he lives. Anyway, so that raises the question about our ethical sensibilities and moral sensibilities. Are they absolutes or are they conventions? And Bertrand Russell, as you might expect, being an atheist, said it's all convention. A fellow Englishman, C.S. Lewis, who wrote on a lot of the same sorts of things, he said they're absolute truths. And for the rest of us, who do we believe? They both have that darn English accent that sounds so authoritative. So we got to go from there. But anyway, so then the last thing I wanted to say about Descartes is that before Descartes, you had algebra, being able to solve things like that. You had geometry, being able to do things like that. And then, of course, it was Descartes' idea that you take this plane and you put a couple axes on it, and then you take this algebraic equation and you can express it as a line, and you take another algebraic equation and that's a line. And then where those two lines intersect is the 0.52, which is what we found with algebra. And so you can do all these things with by marrying together algebra and geometry. Okay. And that started a whole cascade of finding connections for the next 400 years. So, so this is where even those of you who know all about spherical geometry and so on, this might be something you've never really appreciated before. So again, if you want to mention this to your classes, I mention this to my classes all the time. You started with Descartes, who pulled those two things together. And then what did you have that all kind of happened afterward? You had Newton, who said, we have the circular motion, periodic motion of planets, and you have the straight down motion of an apple. And those two things have this commonality, namely gravity. Then soon after that, you had all these things that make up our whole world, gases and liquids and solids and so on. And they all seem so different, but it turns out, no, that's all part of a family. And it's just the number of protons and electrons that make the difference as to which one is which. So there's this commonality again. You have Hertz, who said, we knew about radio waves, we knew about gamma rays, we knew about X-rays, we knew about ultraviolet and such, and of course our visible light. But he was first among others that said, this is all commonality here. It's all part of one big spectrum. And our visible light is just part of this bigger spectrum. One of the questions I love to ask students is what's that next color look like on the right side of a violet, or on the left side of red, infrared or ultraviolet? If our eyes were sensitive enough to see it, what would that color look like? And it's just amazing how little imagination we have to imagine something that's not there. Lucas and Steven Spielberg and so on, they get all this grand accolades for their creativity, but Jabba the Hutt, he's just a big frog, and Chewie's just a big dog and so on. They basically took things that were there and just kind of modified them. But here's where it would take real imagination to think about what's that next color look like. I mean, we can't do it. It's just kind of amazing. We can't do it. Maxwell, what did he do? He took electricity and magnetism and said, those were two things that seem to be different, but nope, it turns out that one makes the other. If you have electricity, you play with it, and it makes magnetism. You take magnetism and play with it, and it turns it into electricity. So that's how the light gets to the earth, by just kind of folding over itself like that. So finally, after all those commonalities, we realized, there's only really two different kinds of things. There's matter, and then there's energy. That's what I learned, in grade school or whatever. And then, of course, along comes Einstein, says, nope, one is just the frozen of the other, with the consequences. So it's still ongoing. Grand unified field theory is basically a way to try to take all these things and say, there's one unified equation that you could put on your T-shirt that would basically capture all these other theories into one, and it would be just one. Maybe string theory is a way to do it. For the mathematicians among us, this is the way I like to explain it. One possibility for our universe is that there is some ultimate equation that you could put on your T-shirt, which is this grand unified field theory. This would be the ultimate equation, which everything else would comprise everything else. And so all these previous attempts that we had from the Greeks, who thought it was what did they think? It was fire and air and water and earth. And then you had Newton, and then you had Einstein, and then you have the Bohr, or not Bohr, but you have quantum mechanics, the Schrodinger, and so on. All of these are just getting closer and closer to that final thing, which we haven't arrived at yet, but maybe we'll get it at some point. So there it is. That's what the sequence is converging to. On the other hand, maybe there is no equation that the sequence is converging to. Maybe the only thing it's converging to is just nature itself. And all we can do is just get better and better at modeling, at describing it. They get better and better predictors, but there is no ultimate equation there itself. So if you're familiar with Cauchy sequences, this would be like a Cauchy sequence. They're getting all these differences are getting smaller and smaller, because There's not much difference anymore between someone post Einstein and Einstein, whereas the difference between Newton and the Greeks was, or I should say, Aristotle was huge. So these differences are becoming less, but they're just getting closer and closer to each other. But there's ultimately no mathematical equation there. All you have is just nature itself that they're getting close to. So one of those, it seems to me, one of those has to be true. Which one is true? Who knows? So that's it. And I got time. I'll say one other thing. This whole idea of finding commonalities also applies to humans. This is something out of the journal Nature of about 15, 17 years ago. Here's the quote. Everybody on Earth descends from somebody who was around as recently as the reign of King Tut, maybe even during the golden age of ancient Greece. You would have to go back in time only 2,000 to 5,000 years, and probably on the low side of that range, to find somebody who could count every person alive today as a descendant. So somewhere in the, say, 3,000 years ago, there was a person living who would have every person alive today as a descendant. So every person alive today would have that person as an ancestor. Furthermore, if you go back a little further, around 5,000 to 7,000 years ago, and this, by the way, this has all been done by studying our genome and such. 5,000 to 7,000 years ago, everybody living today has exactly the same set of ancestors. So this first one is that you just got one person that is a common ancestor of everyone. But if you go back even further, then you got a small set of people. Those are the one and only ancestors of everyone alive today. Only that far, 5,000 to 7,000 years ago. So, oops, doggone it. What happened? There he goes. No matter the language. So here's the editorial after that. No matter the languages we speak or the color of our skin, we share ancestors who planted rice on the banks of the Yangtze, who first domesticated horses on the steppes of the Ukraine, who hunted giant sloths in the forests of North and South America, and who labored to build the Great Pyramids. Olson and his colleagues wrote in the Nature Journal. So anyway, so this whole idea of science finding commonalities comes right down to us as humans. And so I think that's the end of it. Oh, yep, that's another talk. So there you go.
Thank you so much for that talk, Tim. That was really, really great. Very thought-provoking. I really enjoyed it.
Yeah, I agree for sure. Lots of cool stuff there. Fun to think about. I didn't know. So, I mean, you can. There wasn't so much of a question necessarily in the chat, but there was a comment, and maybe I'd let you address it. Someone early on in the talk, when you were discussing non-Euclidean geometry, mentioned that maybe they didn't think that non-Euclidean geometry was that revolutionary, and it was no threat to the absoluteness of Euclid at all. So it's just that Euclid didn't bother to state the obvious. Namely that his truths apply to flat space. And so the person went on to say that they suspected if someone pointed out to him that the interior angles of a triangle on the surface of a sphere don't add to 180, Euclid wouldn't have been impressed with this question. Whatever, so what? So I don't know if you want to respond to the, I have my own personal thoughts, but I don't know a ton about.
Well, I'll say something. I'll let you. By the way, I'll say right off the front, unlike all the other speakers today, everyone else have spent, lots of time researching their particular area. This was something I put together for a non-math audience. So I haven't, studied this stuff any more than what you see right there. So my thoughts are not any more authoritative than anyone else's. But to respond to that question, my guess would be, let's see if you agree or disagree with me, Tom. I would say that Euclid would just not have even considered that to be geometry. He would say, yeah, it may be the case that on a globe, those things add up to something greater than 180, but he would say those aren't straight lines on a globe. Those are curved lines. And so his mind was fixed on a plane. I mean, he was fixed to be thinking about a plane. And so he would have said, no, that's not really even geometry to begin with.
Gotcha. Yeah, Tarina, I don't have much of a background in geometry. Tarina, I don't know if you do or.
No, I don't, but I like the way that Tim put that together and thought about it. So yeah. No,
Yeah.
I don't.
Yeah, I think maybe you're right. But I still think that I think that the changes. So I did maybe agree that with you, Tim, that you could probably wouldn't even have thought about, and that's why he had the fifth axiom there, right? Is that he really thought about straight lines,
right?
But I do think that the work of Gauss and Bolyai and Lobachevsky, I think that was truly revolutionary, right? And has obviously helped change the way we think about things, much as you sort of made the point in your talk about how people come along and really allow people to make advances. I think that was one that really made some advances.
Yeah, that's right. I mean, they're the ones that came up with these other surfaces that had negative curvature and so on. And so it was, and again, this is just the reading I've done. I haven't gone and studied sources or anything like that, but it was Gauss who kind of realized these are all geometries, and it just depends on what the axioms are, and one has no privilege over the other. One has no privilege over the other, and it's very similar, by the way, to the same question that was raised by Cantor when he discovered all these different sizes of infinite, and then the question is, you have, if you take the set of natural numbers and then you look at all the subsets possible from the sets of natural numbers, it's called the power set, then that size of infinity is bigger than the original one. And then if you take that collection and take all collections of subsets of that, you get another. So you have these discrete sizes of infinity. And so then the question is, you've got these discrete sizes of infinity. Each one is bigger than the other. Are there other sizes that are kind of in between them? Mm-hmm. Like you have these discrete integers, 1, 2, 3, but you have all these other numbers that are smeared between them, the real numbers. And so that's the one, of course, that Cantor spent his life trying to figure out, and he never did. He died in an insane asylum, according to lore, maybe wrestling with that problem. And that's the problem that David Hilbert in the year 1900, when he said, okay, mathematics world, we've got a century ahead of us. Let's try to solve these 23 problems. And the very first one on the list are there sizes of infinity between these ones that Cantor has discovered? And it turns out that the answer was discovered in the 20th century. And it turned out the answer is something that no one guessed. I always ask my students, I say, see if you can guess the answer. How many say yes? And some of them raise their hand. How many say no? And I said, you're all wrong. And the answer is, it doesn't matter, that either one of them can lead to a consistent mathematics, just like either kind of fifth axiom is going to lead to a
just like the fifth axiom, take it or leave it. Yep.
Yeah. So really nice parallels there. And I've got some papers on this stuff. I have a paper called Infinity and the Absolute. So again, if there are people who watch this talk and they just want to contact me via my name, Timothy.Pennings@gmail.com, I'll send them a paper, Infinity and the Absolute, and it goes through all this history and so on. So
that's cool.
So it's all there.
Yeah, and I wanted to I should mention too that, I mean, you mentioned, coming to grips with the truth. I think a lot of mathematicians do this on like a regular basis, right? There's like, you encounter it as a student and then you encounter something else. And so you're talking about the fifth postulate here. And I'll mention just my own personal experience that recently I learned, and I should have known this earlier, but I didn't, that the fifth postulate is equivalent to the Pythagorean theorem. So you can actually take the Pythagorean theorem as your axiom.
Interesting.
In geometry and prove the fifth. It's not just a consequence. And
it makes sense. It makes sense.
But I grappled with this for a while, thinking, well, then what are all these proofs of the Pythagorean theorem? They're just restatements of the fifth postulate. Well,
it's just like with the real numbers, right? I haven't studied this stuff in a while, but you can take the
mean value theorem or
one in particular, the least upper bound theorem is equivalent to the Dedekind cuts. There's about 4 different things that once you have one, you got them all.
Even more, yeah.
Yeah,
mean value theorem is one of them for sure. The mean value theorem, yep. So, yep, that's great.
Well, I tell you what, I'm the last one, and so we don't have to go to any certain time. We can cut off whenever. So
Well, yeah, I didn't know. So also, I didn't know if Tarina had any questions, or I didn't know if Tarina wanted to talk anymore about what she's up to. Tarina, I think is late for her. Actually, maybe it's late for you too, Tim, because are you in Michigan?
I'm on Eastern time zone too. Yep.
Oh, so yeah. So for me, it's early. 6:40. I could just keep going, but you
I'm
always
going to bed after this talk,
and, yeah, I don't know.
Tim, I do have a question. So, what drove you to selecting the content you selected for this presentation?
I don't know. I guess. Well, a couple things. First of all, I'm at Davenport University, which is the kinds of talks that faculty give there to each other are talks along the lines of how do we better make a flipped classroom and things like that. Very utilitarian, just things. How do we teach better? How do we whatever, which are all good. But I just thought, boy, in the course of a full day of faculty talks, I want to give them something new to think about, and they go home with something fun to chew on. And so that's why I made these talks in the first place. So then once I decided I wanted something that would be accessible to people and to kind of explain mathematics to all these colleagues who come, from all these areas, then I just used things that were part of my own reading background, things that I'd read over the years or kind of knew about. So it could be that someone could have a talk by the same title and, have lots of different kind of material, maybe different sources and so on. But to me, this fit together pretty well.
I'd agree. Yep.
That's cool. Well, yeah. So I think there was a response to the question too, but so you can go check out the chat afterwards. Maybe someone said something, or the person followed up and said something about how it was strange, maybe that because the Greeks knew that it was a sphere, and so knew that the Earth was a sphere. So why didn't they think why didn't you could think about the fact that all straight lines would be straight lines on a sphere. Sort of strange, I guess, but yeah.
Of course, you've got these different surfaces, but the unique thing about the plane is that all these other ones become a plane locally, right? So you take a sphere and you look at it locally and it's a plane. You look at a saddle, whatever, and locally it's a plane. So there is something unique about Euclidean planar geometry. Gotcha. And if I'm just guessing at this point, but if it was kind of made for the utilitarian reasons of wanting to make houses and pyramids and whatnot, then you can assume the Earth is a plane locally, and so it maybe didn't occur to them to go further. But
well, now you've chimed in a question. I'm going to ask both you and Tarina this. I guess you can both chime in. If you had to guess on the shape of the universe, are you guessing plane? Are you guessing Pringle, right? Hyperbolic, or are you guessing just another sphere somehow that we're on, like a sphere that lives on another sphere? What's your guess? I'll take you both.
Tarina, what do you think?
Oh, I'm going with just another sphere. Yeah. I'm not sure.
Tim, what do you think then?
I think I'd say plane, and I can't remember if I'm up with the latest, but it seems like if I'm not, I might be mistaken on this, but it's as far as they go out, it seems like it's awfully flat. Right. And I think that maybe if it were a sphere or a negative curvature, that maybe they would have been able to detect it by now. But as far as they've gone out, it seems like it's fairly flat. I'm not. I think that's the case.
Yeah, but isn't that also go in line with what you were talking about with the shape, the color spectrum, right? We don't know what's after blue. Yep. Yeah, it's really hard for us to grapple with what we can't see, even as we've been able to see so far. It's very cool. I like it.
I owe you a Snickers bar if I'm wrong.
Someday I'll come and cash in. I'll try to cash in on that one, Tim. Awesome. Well, yeah. So I don't know, unless I didn't know if there was any other questions we have. I think we were going to be joined by Ruth again. I also wanted to pop in before Ruth comes in. I thought I would just mention. First of all, say thanks, Tim, for your talk. I think I enjoyed it. I think Tarina enjoyed it. It was fun to be able to pop in and guess the Fs. Mm-hmm. And I will mention, I saw that I think it was Joyati guessed 4 and then 6. And so I should have been paying attention there. That might have helped me. But I wasn't paying attention. And then, so I guess we can let you go. I didn't know Ruth wanted to chat about some stuff or what we should chat about, but I didn't. You're welcome to stick around too.
I'll stay here with you as long as you continue. That's great.
Sure. Awesome. Yeah. Ruth, I didn't know if you wanted to chime in. Oh yeah.
Well, I don't know if I want to chime in on that. I will say this: I quite like the idea that the universe is hyperbolic, mainly because it looks like a saddle.
I should have asked you to join earlier. Then we would have had that's one of each. That's sphere, flat, and hyperbolic. I'll take it right to the bank. I love it.
Yeah, well, there's no mathematical understanding behind me that really has any kind of authority to say anything about that whatsoever, other than I literally just like the look of it. That's the reason that I like that, and I've always liked that.
And maybe we can get Pringles to sponsor, PMP to help out with the work that you're doing there.
By the way, you mentioned Pringles. Do all of you realize Pringles is the best way for any 8th grade science teacher to explain a laser beam to students, because regular light waves are all different frequencies and they're all jumbled up like a bunch of potato chips. And so you need a bag this big to get 5 ounces. But Pringles, they're all exactly the same wavelength and they're all right lined up together. So you get that much mass just in a little tiny can. So that's what a laser beam is. So there's a
wow,
shout out, a nice analogy.
Wow. Yeah, I like it. Yeah, I didn't really have like these specific things that I wanted to talk about. That's not true. There's a few things that I wanted to say just about like the organization of this event in and of itself. So one thing I do want to say right off the bat is I have to give a huge shout out to Event Squad and Adam. Adam, I won't say your last name out of respect because I haven't asked that, but I will say that Adam at the Event Squad has absolutely been a rock star for us. I feel like he's made us all feel like we know what we're doing, and he's the person behind the scenes, and his company are behind the scenes just making sure that like we're all on time, that all the technology is dope, and everything's just super put together. So he's made me feel as if like I actually knew what I was doing during this process, and I have to say thank you. It's been amazing. So there's that. And if anybody needs any kind of event help, let me just say, Event Squad, make sure you ask for Adam. He's the guy.
Yeah, and I can chime in there too and just mention that, both Tim and I were part of this last year, and Adam was there last year and did a great job with the tools we had last year. But this year, this platform's new for a lot of us to use, but I think it works pretty well, and it's been nice to have the interaction and be able to pop in and out. So I think it's nice to see things changing and evolving right from one year to the next.
I agree. I just sent Adam a note right now. This, from everything I saw, and I was here for most of the day, it just seemed seamless. It just worked very well. I've been to other, and I'm sure you have too, where there's hitches and so on. This worked very well this year. So kudos to Adam and the whole group.
And Ruth, we should say the same to you. I mean, thank you for the organization on the back end. I know that it seems like you and Alyssa Kranz, who was a host earlier, and Glenn really did a lot on the back end to make sure that we had a lot of speakers. I know Christopher, of course, also, right? So Christopher deserves a lot of the organization that he's able to do sort of miraculously from my perspective. I don't understand how Christopher is able to organize a lot of things that he does, but then sort of, Alyssa and you and getting people sort of organized, getting the speakers, getting different hosts to chime in. And it's been a lot of fun this year to have a little bit more of that community feel with people popping in and out.
Yeah, well, the Pi Day is a big deal for us. I mean, it's a thing. I don't know how else to say it. It's a big deal. It's a big deal for Christopher. It's a big deal for all of us. And I think it's just a great excuse to be able to get together and meet people with a common interest. For me, I'm highly social, and I mean highly social. So I absolutely love the idea of just connecting with people. I love the chat. I definitely want chat. I don't care how antiquated that it gets or what kind of rap it gets moving forward, but I'm telling you, I want to chat in every event that I go to. I quite like the idea of being able to put comments up there, and that's really just a thing. And we work hard on this. There's a lot of people behind the scenes that individuals never get to meet. I mean, we have a board of directors that's just amazing, and we have just tons of volunteers. I don't know if you guys realize this, but we have almost 400 volunteers, and it's a big thing. It's not just one or two people. I mean, we have people that are just, all over the globe that are helping us out in some way, shape, or form. And it's quite humbling, and it makes me feel like a small little guppy in a really big ocean full of fish. And so, but I would like to just add in there too, though, that's really the joy of like inclusivity, is that you get to bring people together at all levels of mathematics and from all walks of life, from all different planes of the earth. And I think that's important. As somebody who's transgender and went through the prison system, opportunities weren't very abundant for me. And the opportunities that I did have, I had to sort of scrap for them. And I had to, I had to get really crafty as far as being able to present myself as somebody who was worthy of the opportunity. And it's nice to be able to take something like this and then just consistently put out the effort to try to bring it in. And that actually brings me to a point of like an idea of something. I wanted to sort of pitch this out to people, that we would like to have some sort of a submission of inclusivity-based papers in mathematics. So it's going to be intentionally left vague about what that actually is, because we want people from all walks of life, both that are incarcerated and in the free world, some who have never had any kind of interaction with the prison, the system at all, and then those that have. We'd like to get opinions and these op-ed pieces or studies or papers about inclusivity in the mathematical community. And then if you could just mail them to us. Adam, do you still have our address that you can put up there? So just, you can mail it here, and you can put just attention Ruth. Or for those of you that are in the free world, you can email me at some point and we can give you a little bit more direction if you'd like, or just submit them at ruth@pmathp.org. So
very cool.
And we'll
and
release
Ruth,
more details about that.
Yeah, and Ruth, I don't know if you know about it, but do you know about the Journal of Humanistic Mathematics? That sounds like something that could make its way to a special issue of the Journal of Humanistic Mathematics. I don't want to speak for the organizers there. It's a fantastic resource for people. The Journal of Humanistic Mathematics, it's freely available, download online. There's a lot of great pieces, just all sorts of stuff. Kind of some of it in line with what you're talking about, some other stuff. So they take a lot of stuff. And it's one of my favorite resources online for looking at what people are doing that's not kind of just down the mainstream all the time. So pretty cool.
No, I hadn't heard about that. I'm going to look at that as soon as we're done here. I'm interested to see if Christopher's heard about that either.
Okay, yeah. That's cool. I don't know, Tim and Tarina, have you heard of the Journal of Humanistic Mathematics?
I don't think I have.
Okay. Yeah, I would check it out. I think they've had over like 500,000 downloads since it ever started. I don't know how long it's been around, but probably at least a decade, but maybe longer.
Wow. Okay. Wow.
Cool. Well, yeah. So I don't know. I don't know what else we have. I will remind people that I think one of the things that's nice about this event is just to try to make it known that the PMP is available to work with. So if you're a mathematician and you want to connect with somebody, or even if you don't consider yourself a mathematician, but you want to connect with somebody, then you probably are a mathematician. And so, you should try to figure out how to be involved the best you can, right? So hopefully we can all get involved one way or another. I didn't know if you had any other ways for people to be involved at all, Ruth.
Yeah, no, we absolutely need more help. We need more volunteers. We need more mentors. We need more participants. We need more support, and just in all kinds of ways. So just a few fun little facts. Since we've had this event today, we've had 2 new participants sign up. We've had 2 new requests for participants to sign up. They've contacted us via the email system. So we're going to get them signed up ASAP. We've had 10 new mentors sign up. And that's just from what I can see from the last check, like an hour ago. We've raised almost $1,000, which is so appreciated. And we're just so excited for everything that's happening here. So yeah, people that want to get involved, there's lots of ways to get involved. For instance, just to give like a quick side about how that can happen in other ways. We had a mentor sign up, and one of his interests were he was really into computer programming, but he had this very sort of specific niche thing that we wanted to talk about. So we asked him about it. He was willing to help us out with other projects. So we asked him about it. Now he's somebody that really helps us behind the scenes in our tech. And he's also been a major support for us to get the coding project off the ground. You know, part of what we want to do is bring computer programming and really all of STEM to a restricted learning environment, which means that we have lots of like little intricacies that we have to navigate around. And I don't know if people were able to see on Mitsa High earlier, but you know, that's kind of a tricky process to teach somebody without a laptop or a computer how to computer program. But we figured out how to do it. We figured out how that we can teach at least the fundamentals of that. I think that's really important work. So this mentor, who's now a part of our team, you know, he's instrumental in that, and you know, he's one of several people that are instrumental in that, of really just sort of putting that together. And then we have lots of projects that we'd like to get kicked off, but we can't do that unless we have, you know, people that are willing to sort of put boots in the ground and say, okay, here I am, I'm ready to do this thing. So yeah, there's always ways for people to get involved. And as we expand out into STEM, like full STEM, we need individuals that have, one, diverse backgrounds, but two, can teach a complex topic in really simplistic terms and really complex terms. You know, we have somebody who's studying complex analysis who's, I mean, I gotta say, he's somebody that's really difficult to keep up with as far as intellect is concerned. And then we have individuals that are just starting out. So we need people from all walks of life. There's people out there right now that are scared to get involved with mathematics because they feel like it's not for them. And it's just not true. But it's the same thing with physics or chemistry or computer programming or anything. And so the more of a diverse group of people we have to choose from to sort of like pair people up with, then the more we can attract individuals so they can get access to this thing that some of them have been told their entire lives that it just wasn't for them, that they're not smart, they're not intelligent. If they were smart, they would have been born with it. And, you know, we know that's just not true. You have to work at this stuff, and sometimes you have to speak the language of somebody who's never had access to it. A little bit more patience, and just a little bit more love, and just a little bit more understanding that everybody's intelligent.
And Ruth, in line with that, I want, just for the record, I want to read something that you've all seen, because Christopher wrote it to us yesterday, but since he can't be here with us, here's what he wrote, and this is beautiful. Tomorrow we will make something beautiful happen together and share it. He continues, part of our push for inclusivity includes shining light into dark places so that we may project the image of our passions and love for this wonderful world of mathematics. I've been shown beauty, found truth, and come to know love through study combined with a culture and community that exists around math. Listen, I've been shown beauty, found truth, and come to know love through the study that exists around math. The transformative process I've experienced, there aren't words to describe it sufficiently, but we can share it by continuing to help others find similar experiences. So that's his passion right there. And it's just really cool that there are, as you said, Ruth, hundreds of people that are all part of this vision now.
Yeah. You know, I like to think about it in terms of like what's possible. Like what's possible. For one, I was told that most of the things that I was able to accomplish while I was incarcerated were impossible. It was impossible that I was going to be able to transition while I was incarcerated. It was impossible that I was going to be able to publish in anything other than maybe my own blog. It was impossible that I was going to be able to get an education. It was impossible that I was going home. I was given a life sentence. It was impossible that everything was impossible. And what I like to think about is, I know everything that's impossible, but what about the things that are possible? And I like to think about that in terms of people, because I think people are possible. And I wonder how many more Christophers are out there. Christopher wasn't something that was uncovered. Christopher created. He was created. He took the time to bring himself to that point, and it's because he had help. He had a drive. He had a passion. He had help. And I wonder how many other people are waiting to be helped to walk into this world as this new version of themselves, and as a created version of themselves, their ideal self. And it's that self-actualization, that self-identity. I wonder how many more are out there. And I'd venture to say that there's 2.3 million people incarcerated in the United States, just the United States. And by the way, we've expanded into Canada and Europe. We're coming for you too. And just as like for the end of the year goals there, I'm just going to go ahead and project that out there. And I wonder how many people are out there waiting for somebody to just step in the light and say, hey, listen, here we are. We're that light on top of a hill. We want to talk to you. We want to help you. We don't care where you're at. We just want to meet you right where you're at, and we want to help you create whoever you are. Let's do it. Let's get in the mud. Let's make it happen.
Very cool. Oh yeah. So I don't know. I see we're at this thing says we're almost at 10 hours, right? That's a long day. Like I said, I know Tim and Tarina are on the East Coast, so we're coming up on 10 o'clock at night, right? It's even going all day.
Yep.
Yeah. But so I don't know if we should call it quits at 7 and say, hey, it's been a success.
Very good.
Yeah.
Awesome. Well, yeah. So thanks everyone. And thanks.
Trina, nice to meet you.
Nice to meet you as well, Tim and Tom and Ruth.
Yeah.
Awesome.
Yeah. If anybody has any questions moving forward, just feel free to email us over there at the PMP. Log on to the site. You'll be able to email us on the contact page. I'll be there. And then of course, for all you mathematicians out there, make sure that you watch that inbox, because you may just get an invite to come do some crazy project with us. And I promise it'll be fun.